This over here. This over here. Oops. Come on. All right, you guys should see a screen in front of you that says 2.4 exact equations, right? Okay. All right, yeah, so our goal in this section is to study these first order equations that are said to be exact. So first, let me give you an idea of what they look like. So I'm going to skip down here and show you some example problems. So first of all, this is a differential equation. It looks a little funny. Probably what looks a little funny is that you can definitely see the dy and the dx, but they're broken up. It's almost like we're treating the dy dx as if they were the numerator and denominator were variables. In fact, look at this problem right here. This is a very similar. This is a first order differential equation, and so is this one. The only difference between them is that this one right here is expressed in what we call differential form. So differential form basically is when you kind of treat the dy and the dx like dy over dx like fractions, which you can do in some situations. And then you're going to basically kind of separate variables in a sense. We already kind of know how to do this, but we're going to put all the variables on one side like so. Okay. So it turns out that this is useful for solving these types of equations. And in fact, some of these, not all of them, but some of them will be what we call exact equations. There's going to be a condition on this and a condition on that. And if both conditions are met, then the equation is exact, and that will guarantee that there's a solution, and we'll talk about how to find it, okay? So yeah, the big picture is we're going to be working with equations that look like this. So even when they look like this, you're going to reorganize them so they look like that. Okay, so let's start off with an introduction. So again, we're solving exact first order equations. So the idea is that we're going to find a function of two variables. We'll call it capital F, doesn't matter, whose what we call total differential, I'll explain what that means in a second, matches the exact differential equation in differential form. Okay, so that's a lot. Doesn't really make sense yet, but that's okay. But I will tell you this, once you find that function F here, you're going to set F equal to C. And once you set F equal to C, this is going to be the general solution to your differential equation. And it's going to be implicit, right? Because y is not solved for. You can make it explicit by solving for y if you like. All right, so we're going to kind of build up the motivation or the theory. So here's the idea. We're going to kind of work backwards. Let's say that we start off with the solution. Usually you start with a problem and then you find the solution, right? But I want to build up the theory to this. So why don't we start with the solution and build up to the problem? And then whenever we have that problem statement, all the steps are reversible, and then we'll know that you know, our starting premise is our solution. So for example, let's start off with this this implicit equation right here. And then I'm gonna build it up. So there's no derivatives involved here. So I'm gonna build this into a question involving derivatives. So first of all, note that C is an arbitrary constant, and also we're treating y as a function of x so that y is the dependent variable. All right, now I want to build a differential equation out of this. So this is going to involve derivatives. So clearly we're going to take derivatives, right? So why don't we do this? Why don't we take both sides of the equation, or you could just say the equation, and we'll differentiate both sides with respect to x. Now the left-hand side is easy. if you apply the differential operator to the constant c, you just get 0 out. The left-hand side is a little trickier because you're going to apply the differential operator to the function f. And f itself is dependent on x and y. But remember, y is dependent on x. Okay? All right, so really what this comes down to is I've got the 0 on the right, that's fine. And then on the left, I have this derivative here. So basically, I'm differentiating the f function. I don't have to show the full function form if I don't want to. It's just df dx, d capital F dx. So we handled these types of derivatives back in Calc 3 when we dealt with functions of more than one variable and those functions depended on other variables. So we used the chain rule. It's a three-dimensional version of our chain rule from Calc 1. So if you just kind of look at the logic here, look, f itself, we don't know what f is. That's what we're trying to find, right? It's actually what we started with, but it's some function, right? So let's take f and let's differentiate it. F depends on two variables. It depends on an x and a y. So do I have to use partial derivatives here or ordinary derivatives? Which is more appropriate? Yeah, it has to be partials, right? So you'll notice f depends on two variables. So you can't use an ordinary derivative because ordinary derivatives, you can only have one input variable. And then usually like we'll use like a prime or you could use Leibniz notation. But when you're dealing with partials, the reason why we have to deal with partials because f depends on two variables. So you literally have to tell me which variable you're differentiating with respect to. You can't just say prime. It's arbitrary. It would be ambiguous if you said that. I would have to ask you a follow-up question. Well, what variable do you mean? So in this case, we've got an x and a y. So I'll write my tree diagram like so. And x is going to stop right there. However, remember, y is actually dependent on x, right? So it's implicitly dependent on x. So what I'll do is I'll draw a little arrow below that down to x. All right, so if you remember the chain rule back from Calculus 3, the idea is, let's say that you want to find df dx. Let's make sure we understand the notation. Is that an ordinary derivative there, or is that a partial? That's an ordinary. So you want to ask yourself, why are we using an ordinary? Look at the picture. It might give it away if you look at the picture. Anyone know why we're using an ordinary and not a partial here? Yeah, look, that's it, Sergio. So look, yeah, I would call this row here, or these two variables, I would say this row, it's kind of like an intermediate step. But look, f ultimately depends on one variable, right? If you go down this chain, it ultimately depends on x. And if you go down this chain, it ultimately depends on x. So there's really, if you ignore the intermediate y value, f depends on one variable alone. So f, capital F, is really a function of one variable. Okay, so that's why we're using an ordinary derivative, df dx. Now, along the way, we take a pit stop with this kind of intermediate variable, and that's okay. Let's actually use the chain rule to see if we can come up with a formula for df dx. You guys did this back in Calc 3. The idea is you're going to go through each chain to get to x. So I see two chains. I see one chain here. So what you're going to do is write down the rate of change of this variable with respect to that variable. And that itself is a partial. It's the partial of f with respect to x, which goes right there. That's one chain. And then we're going to come up with all the other chains. And there's really only one other chain here. It's this one. And you're going to add this chain to the one we already did. So there's going to be a plus there. And you just go down, find the product. So this is a partial, the partial of f with respect to y. And so I'll write it. So there's the partial of f with respect to y. But then I have to multiply by, this is an ordinary derivative, right? Because y depends only on one variable. So I'll write a dy dx there. Is that okay? Does this look a little bit familiar for those of you guys that took Calc 3? Maybe not. Okay. Yeah, you guys learned this at one point. It's just the chain rule. It's a higher dimensional version of the chain rule from Calc 1. The chain rule is the most used differentiation rule in all of calculus, right? Because this is when you have functions within functions, and that's pretty much all functions you're going to work with, except for the super basic ones. But pretty much everything we work with is functions within functions. Okay, so what we have is an expression for the derivative of f with respect to x. Remember, f is the thing that we're after. That's actually, I should say, this is the thing we're starting with, right? But we're building a differential equation. So look, I've got this equation. I know it's true. It's kind of looking more like a differential equation now. Let's keep building on it. Let's plug this expression for df dx. I'll plug it in to the left-hand side right there. That's the same thing, right? df dx is the same thing as that. Okay, so if you plug it in, then we're going to get this equation. Okay. Now, remember, the whole point is to build a question. We started with an answer. We're building the question. Okay, it looks a little weird. Why don't we do this? Why don't we multiply both sides by dx? We're treating the dx and dy's as differentials. So we'll just multiply both sides. If we multiply through, the dx doesn't do anything to the right. But over here, let's see, we've got a dx there, got a dx here. Do you see these dx's will cancel? If we treat them like dx, like differentials, variables, right, they'll cancel. And then we've got this differential equation. All right, so we've created the question, right? So if you start with this equation, which is not a differential equation, it's just some curves that implicitly define functions of x, and then I build a question out of it, build a differential equation out of it, then it's going to look like this. Okay, so here's where we put it together. Look, let's say that you're given a differential equation in like some problem statement, and you can rewrite it in what we call differential form, right? So you put a 0 on one side, and then you have your dx's first and then your dy's, and you could read that first coefficient as the function m, and we'll call this the function n. So let's say you're given that problem, and let's say it happens to be the case that this function m is the partial of some function of x some function f with respect to x, and it happens to be the case that n is the partial of some function f with respect to y. If that happens, right, then that means there exists a function f where that happens. That means all the steps are reversible. That means you can go back to the beginning, and that means that there's your solution. Okay, the logic's weird. You probably never really worked with something like this before, but essentially we're building the question, and then whenever you run across a problem that looks like this, as long as this has that property, and as long as this has that property, for some function f, right? You don't know what the function is, but if you do, if you can find it, then all the steps are reversible, and then you could just write down the function equal to c. You have to write equal to c here. I noticed this last semester. A lot of students didn't write that, and that's a problem. If you forget this part, then that's not really a solution, right? A solution is y equals a function of x. It's an equation, right? So that's not an equation. That's just a function of two variables. Okay, so that's the idea. This is a cool trick. If it works, right? It only works if these two things happen. So you have to figure out if a function f exists that does that. So let's start off with a real basic one. We're going to use this definition. If you start with a function capital F of two variables, we're going to define something called the total differential, which we're going to designate as a df this way. Is that okay? Now you might wonder where this came from. It just comes from right here. Here, let me go up here. It comes from hold on, df dx comes from right here, right? Comes from, using the chain rule. So then you just multiply both sides by dx. And then you can rewrite it so it has this nice form. So it's just a definition, but if you divide by dx here, you can get back, divide by dx here, and divide by dx here. You can get back to that result we had for the chain rule. So this is gone, and then we have that chain rule result we had earlier. Okay, so let's jump into a problem. All right, so we've got two things to do. First of all, I've got this function I'm giving you. This is a function of two variables, which is the surface in R3 if you wanted to graph it. Let's start off by finding the total differential of this function. So to find the total differential, we're going to use this formula. When we say total differential, that's what we mean, right? df. It's not the same thing as df over dx. It's just df by itself. It's the differential by itself. All right, well, here's the formula for it. So there's two things we have to find. We have to find this one and this one. That's all we really have to do, because that's all we know is f, right? We know f, and then we take the partial of f with respect to x. So we'll start there. That means you're going to apply the partial differential operator to the function f. And then over here, we're going to apply the partial differential operator to the function f again. In the first case, we're partial differentiating with respect to x. In the second case, we're partial differentiating with respect to y. Are you guys following the logic here? Yeah, okay. All right, let's keep going. Okay, so now this is partial derivatives. This is Calc 3 stuff, right? Partial derivatives. However, we do use it a little bit in this class. I know I said this was a class in ordinary derivatives, but partials do show up from time to time. We don't do PDEs though, thankfully. That's a later class. But yeah, you should be familiar with partials. And we've already done it once with that existence and uniqueness theorem in section 1.2. We took the partial of a function with respect to y. So we'll take the partial of this one with respect to x. So if you're having issues taking partials, you might want to stay after class and we can talk about it. But basically, the idea is if you partial differentiate with respect to x, you treat y like it's a constant. So just kind of pretend in your head like it's a constant and just treat the x's like normal, in which case you'll get this. And then we can do the same thing with this one. And there's your derivative there. Is that okay? If you're having issue with partials, definitely stay after class. We need to get that taken care of because we're going to be doing lots of that here. So that's going to hold you back if you're having issues. Okay, so we got part A done. We found the total differential for this function. There it is. Here's our total differential. All right, now an unrelated problem. We're gonna take this differential equation and we're going to move it into it's called differential or total differential form. So we're just gonna move it around. We know what it's kind of supposed to look like, right? It's supposed to look like this. 0 on the right, and then you got your dx term first and your dy term second. So fairly easy to do. You just take your differential equation and you kind of treat the dy and dx as if it was an actual fraction where dy and dx are both variables, which we call differentials. So multiply both sides by, say, 2x and both sides by 2x squared y, and then you can kind of kill the fractions or kill the rational expressions, and then subtract the or add dx to both sides so that we have our original differential equation now in what we call differential form. Is that okay? Okay, so now the third part is asking us, okay, well, can we make any conclusions? Well, look, I gave you this kind of function out of the blue, and we found its total differential. And then an unrelated note, I gave you this differential equation and we found its total differential form. Look at the total differential of f, and then look at the left-hand side of our equation, which is in differential form. They're the same thing, right? Okay, so I would say that it just happens to be the case that the partial of f with respect to x equals this guy, and the partial of f with respect to y equals this guy. So that's what we were kind of mentioning up here. If it happens to be this case, then we know that we know what the general solution is. Let me clean this up. Yeah, so we know what the general solution is. So what we do is we just go back to our original function f, and we just set it equal to c, where c is any arbitrary constant. So I'll take f, here it is, and I'll set it equal to c, and there is our general solution to this differential equation. All right, it'll give us all possible solutions.
Professor?
Yeah.
Kind of a, I don't know, technical question here, but why, when it's dy dx, did that become negative? Like in part B right there?
Oh,
From where we started?
oh, here?
Yeah, so how did that become a negative? Just curious.
Oh, I moved the dx to the right, and then I multiplied 2x squared y to the left, and I just kept this negative where it's at.
I guess I don't see where the negative came from, just from the beginning.
Oh, did I mess up? Oh, no, here it is. It's given in the problem statement.
I see.
Yeah.
Okay.
So, is that okay?
Part of this. No, I thought we started with the f of xy. Got it. Okay, thank you.
Oh, yeah. There's two different problems here. For part A, you're finding the total differential of that guy. And then for part B, which is kind of unrelated, you're just finding the differential form of an unrelated equation, which happens to be related, you find out, right?
Yeah.
But yeah, okay. So yeah, this is not,
thank you.
No problem. Yeah, this is not usually how we're gonna do these problems. Usually you're not gonna be given the solution, right? So yeah, we'll build our way up. But just so you know, if you take that f function and you set it equal to c, you'll get the solutions and you'll get a general solution. It's implicit, right? You could solve for y, but you'd get two functions. So let's just leave it like it is. So what we have is a implicit general solution. You guys could graph these on Desmos if you wanted to. You could just plug that in. We did some work on that last week. Here's the solution in the language that I use. So this is for c values of 1, 2, 3, and 4. You'll notice that I'm removing points where y is equal to 0, and you might be able to guess why, right? The slope goes vertical at those points. Also, x equals 0. X can't be 0, so there's no solutions here. So but there's no curve there, so I didn't have to remove it, right? But if you want to play around with it, you guys have the same file, and then you can play around with a particular solution, kind of move this around, see what happens, right? Like, for example, this is technically 4 solutions, right? You got one here, you got one here, and one there, right? So if you had like an initial value problem and you picked a point, you'd have to pick one of these curves. And if it was up here, you would move the curve around until you got to that point, maybe right there. And then that would be your solution curve. Okay, so it's nice to graph these, you can kind of have an idea of what the solutions look like. All right, so yeah, but that's not really how the problems are going to work. This is just more motivation as far as what we're going to be doing. So let's talk about exactness. So this little process only works if there exists a function f so that the partials with respect to y and x match up with x and y match up with m and n, respectively. So we're going to give that a name. We're going to call it exactness. Okay, so if you have a differential equation like so written in total differential form or just differential form, we say that it's exact if there exists a function f so that the partial of f with respect to x equals n and the partial of f with respect to y equals n. That's what it means to be an exact differential equation. And these are the only ones that we'll be able to solve using this method. The kind of crappy thing about this is it doesn't tell us what f is. And that's the hard part, right? So that's not really going to help for like a test. So, but maybe there is some kind of other test we could use that would be quick and we wouldn't have to waste our time trying to find f. All right, is there a test? Well, yeah, so it's called the test for exactness. And it goes like this. You take your equation and you write it in total differential form like so. And you can tell if it's exact if you take the partial of m with respect to y, and then you take the partial of n with respect to x. And if those guys are equal to each other, then you can conclude that the equation is exact. And if it's exact, then these two things must hold. Okay, so we're going to test for exactness, and then once you test for exactness, you'll have confidence that there's a solution. So let's look at an example. So here's a differential equation. The first thing you want to do is identify the m function and the n function. The m function is the one in front of the dx. So you always put this one first. There's your m function right there. The n function is the function in front of the dy. So that's your n function. So it's alphabetical, right? So you got x's, then y's, m's, then n's. Okay. All right. So now what we like to do before we try, doing any work here, it would be nice if there was this test we could use to see if it's exact, because that's going to save us some time. So you don't want to go looking for a solution if you don't know it exists. And it turns out to be a little bit of work trying to find it. I'll show you in a second. So what you're going to do is take the partial of m, which is this guy, with respect to y, which is the other variable, right? So you're going to take the partial of m with respect to y, and then you're going to take the partial of n with respect to the other variable, which is x. And if you get the same thing, then it's an exact equation, which basically means it's solvable using this method. Okay, so we can do this quickly in our head. If you want to take the partial of this with respect to y, then you treat x like a constant. So it looks like you're going to get 4xy there. Is that okay? The derivative of this with respect to y. Was that okay? Okay. And then we'll do the same thing here, and we'll take the partial of n with respect to x, and you also get 4xy. Okay, so since they're the same, we can conclude that there exists a function f so that if we take f and we set it equal to c, that it's a general solution. All right, so this is pretty comforting, right? Makes us feel good. At least we know that there's that this solution we're after exists. But at the same time, we still got to find f, and that requires some work. That's what we're finally going to talk about. This is the bulk of the work for this section. So the way we're going to handle finding f is we're going to use a technique which is very similar to what we did in Calc 3 when we worked with vector fields and we found conservative vector fields that had potential functions, finding a potential function. Does that sound familiar at all, finding potential functions of a vector field? Okay, a little bit. All right, well, it was at the very end of Calc 3, the last chapter, and it's a little tricky, but this technique is pretty much the same. So here's the procedure. So first of all, you have to start with an exact differential equation. You guys know how to test for exactness, okay? So don't do this procedure unless you know for sure it's exact first. Okay, so once you know it's exact, what that means by definition of exact, it means that there does exist a function f such that the partial of f with respect to x equals m. So you'll know that this is true. And you also know that for the same function f, the partial of f with respect to y is equal to n, which is this guy. So that's by definition of exactness. You guys okay? Okay. All right, so here's where the notation comes in. So you're going to pick one of these. It doesn't matter which one. And we're going to start with that one. So for example, let's start with this one. Our goal is to find capital F. Okay, so let's think about this. If I've got this known equation and my goal is to find capital F, because once I'm done, I just take F equal to C and I'm done, right? What do you think I'm going to do to this equation in order to get F, to get closer to capital F? What should I do to it? You should integrate, right? And more specifically, we should probably integrate with respect to X. Yeah. So when you guys get good at notation, so as your notation strengthens, what you'll find is you won't even need to memorize this procedure. The notation will suggest what you need to do. I mean, our goal is to find F. And so if you get here and you say, I have to find F, you just think, oh, I have to integrate. So there's your first step. So use the notation to back up the concept, use the concept to back up the notation, and they help each other. Then you don't have to memorize useless formulas like this. This is fairly useless. You don't need to memorize this, but I'm going to walk through it anyway with you. Okay, so we're using this equation. So we're going to integrate both sides of this equation with respect to X. So I'm going to throw on some integral signs, and I'm going to integrate with respect to X. Throw on a little dx there. Okay, the left is easy because you're starting with F, partial differentiating with respect to X and integrating with respect to X. They undo each other, so you have an F on the left. And on the right, well, this is something that you can evaluate. You guys can do this, right? If I give you that function m, whatever it is, you guys could do the integral. Hopefully not a tricky one, right? Some of them are more tricky than others, but you guys can do that work. Now, something funny is happening. Normally, there would be a plus c, and the plus c comes from both sides of the equation. You absorb it on one side. But in this case, you'll notice there's a plus g of y. So what's going on there? Well, the g of y is kind of like our arbitrary constant. It really is a constant. It's just that when you integrate with respect to x, you're treating y like a constant, and we integrated with respect to x on both sides. So I can't just write a plus c. That's not good enough. And the reason why is because y is also a constant as far as that integration was concerned. All right, it's very easy to check. Just differentiate both sides of this. Let's say you wanted to get back to here. Just differentiate both sides with respect to x. So on the left, you get this, and on the right, you'd get this. And it can be any function of y. When you differentiate any function of y, it doesn't matter what it is. It could be cosine y plus 17. It could be y squared plus y minus 4. It doesn't matter. All the y's get killed anyway. So this is, in fact, acting like our constant of integration. It can be any function of y. Okay, let's keep going. Now, our goal is to find f, because once we find f, we're going to set it equal to c and we'll be done. We've just about got it. I'd say we're about halfway done. This is f. You guys can evaluate that integral, so that's fine. But the only thing we don't know is we don't know g of y. So we still need to find what that function g of y is. And once we find g of y, we'll be done. Just plug it in here, and then you got f, set f equal to c, and you've got the solution. Okay, so the question now is, how do you find g of y? Well, look, we've already used one part of exactness, but we have this other part that we haven't used yet. So in general, you want to use all the parts that you're given, when you're working through these problems. So perhaps this is going to come up somewhere, right? Perhaps this is going to come up. All right, so why don't we do this? We're pretty much halfway there. We've got f, except we still need to know that. Once we know that, we'll be done. So why don't we do this? Why don't we take this equation and we'll take the partial of f with respect to y. And the reason why we're going to do that is because what I get for a result must equal this. So I'm going to take my result and set it equal to this. So I'm going to take this equation and let's partial differentiate. So on the left, got the partial of f with respect to y. And on the right, I'm going to take the partial of the entire side. I can break this across a sum. You guys can do this part, I think. I know it looks ugly, but once the m's in there, you guys can do the work. So that's not hard at all. But then when you take the partial of the g of y function, there's no x involved, so you might as well use a single prime there. It doesn't make a difference. Right? So use prime because it's already a function entirely of y. So when you take the partial with respect to y, it's an ordinary derivative effectively. Okay, so now I've got an expression for the partial of f with respect to y. But we already know that the partial of f with respect to y has to equal n. So if I know this is an expression for the partial of f with respect to y, and I know this is an expression with the partial of f with respect to y, and that means they have to be the same thing. So let's set them equal to each other. So if we set them equal to each other, what's going to happen is you're going to set this guy equal to this guy. This is going to be some function, which you guys are going to be given. This guy you can evaluate yourself. It'll be easy. And you're going to have this g prime sitting around there. Our goal is to find g of y, right? That's the one last thing we had to find. So I think we can take this equation, solve for g prime of y, and then maybe solve that little mini differential equation, solve it for g of y, and then we'll have our solution for f. And then once you have f, set it equal to c, and then you'll have your general solution. Okay, I've walked you through the theory. I know you probably are like, let's do a problem. I totally get that, but I have to show you the theory too. It's important. So let's jump in and do one. All right, let's start with this one. This is a first order differential equation. It's already written in differential form, which certainly suggests that we should see if it's exact. If it's not exact, then, we still have a couple other methods. What are our other methods again? We have for first orders. We could separate. I don't think that's going to work here. Yeah. And then we have linear first order. This one I don't think is linear. And you also have direct integration, so that's not going to work either. So yeah, but this is a section on exact equations, so let's jump in. All right, so the first thing you want to do is check to see whether it's an exact equation. So we're going to take the partial of this function, which we call m, right, with respect to y, and then we'll take the partial of n with respect to x, and those have to be equal. That's the test. So let's do that first. We'll take here's m and here's n. So we'll take the partial of m with respect to y and the partial of n with respect to x. And what you'll notice is they are the same. You get 2x in both cases. Is that okay? Okay. All right, so now we know that it's an exact equation. What that tells us is that there is an f that exists, a capital F. So we'll be able to find it using that procedure above. And at the very end, we'll just take f and we'll set it equal to c, and that will be all the solutions. Okay, so now we know it exists. At least we have some confidence in what we're doing, right? All right, so since we know f exists, we know two things, right? Because it's exact, we know the partial of f with respect to x equals m. And we also know the partial of f with respect to y equals n. That's by definition. Okay, but you're given m and you're given n because this is an actual problem, right? Okay, so now you want to pick one, right? You can do the first one, you could do this one first. And then you could do this one, or you could do it in the reverse order. I'm just going to go in the same order, same chronological order. Let's start with this one. Okay, so this is something that we know is true. Now, my goal is to find f. So what do you think we should do to both sides of this equation? I can get rid of this m here. I don't need to put that in there. You guys get it, right? All right, so what am I going to do to both sides of this equation to get at f? Yeah, we're going to integrate with respect to x, right? Okay, so what you're telling me is you don't need the procedure above, right? If you think about it, you don't really need it. The notation's telling you what to do. That's the nice thing about notation. So yeah, so we're going to start off by integrating this equation with respect to x, both sides. So on the left, we'll have that on the left, and on the right, we'll have this. So if you integrate a derivative, you get back the original function up to a constant, but we're going to absorb the constants to the right. And on the right-hand side, if you integrate 2xy with respect to x, you get x squared y, and then negative secant squared is minus tan x. And then there's that important part, which is really technically important, right? The constants on both sides happen to be functions of y. So make sure you put a plus g of y there. So we're kind of halfway done, right?
Will g of y have a value, or will it just be like g of y?
Yeah, you actually don't know what it is. So that's why I'm naming it g. We don't know what the function is, but we're going to find it.
Got it.
Yeah. So I'll put a little question mark there. We know it's some function. We just don't know what it is yet. All right, but we're halfway there, right? So, we pretty much have F. Once we find G, we can plug it in. That will give us F, and then we set F equal to C, and that will be our general solution to the original differential equation. So we got to find G. What we haven't used yet is this equation. We used the first equation, but we haven't used this one. So think about how you might use this. Well, in order to use it, you're going to have the partial of F with respect to Y, which suggests that maybe I should take this equation and differentiate with respect to Y, and then set it equal to this one. You follow the logic here? I'm not even thinking about the procedure. I'm just looking at the notations telling me what to do. You guys can follow the procedure, and that's probably good at first, but over time you'll find out that you don't need to. The notation's telling you what to do. So let's take our function that we're after, which we're almost done with, right? All we need to do is find g of y, but let's differentiate with respect to y, both sides. So then you have this equation. And notice when you get to the y, the g of y function, and you differentiate, you can treat it like an ordinary derivative, g prime of y. Okay, and then look, so on the left side of this thing, I'm gonna basically equate the two equations, right? So I'm gonna equate this one, x squared plus 2y, and this one x squared plus g prime of y. I know they have to be equal because they're both the partial of f with respect to y. So we'll set them equal to each other. And now I've got this differential equation, this new differential equation. And if you cancel the x squareds, you'll notice that this is a differential equation with dependent variable g and independent variable y. So it's kind of like a new differential equation within the big one that we're solving. And this one, we're just going to solve for g. That's all we're trying to find. So this one, just use direct integration, techniques. Just integrate both sides with respect to y. So just do this. So integrate both sides with respect to y. So on the left, you have g of y, and on the right, you have y squared. Now, you notice that I left off the plus c there. You guys are free to put it in, but you really don't need it. And the reason why you don't need it is because, look, we're going to take our function f. Remember this guy? Now that we know what g of y is, we can simply plug it in. And yeah, technically there's a plus c there, but it doesn't matter because we're going to be setting it equal to c anyway. And then the c gets absorbed to the other side. So it technically doesn't matter if you put that c in there. Okay, so here we go. There's our general solution to the original differential equation, which is given right there. Okay, does that game plan, does that make sense? Yeah, see if you do it a few times and then see if you can think about the theory. Think about it. We're kind of working backwards, right? That's kind of the idea. But it works. All right, and if you wanted to see like a family or see this the general solution or a set of family of these solutions, I made some on Desmos. This is what they look like. This is in the XY plane. Of course, you'd want to remove all points for which the graph goes vertical. So you'd probably want to remove a point there, probably right about there, right there. What you could do if you're interested is you could kind of study or analyze this graph, and you could, try and figure out why things go vertical and why things go flat based upon this. You might want to rearrange it so it's dy dx equals something. And then you'll kind of be able to tell why things happen the way they do. So you're free to mess around with that, but you don't have to. All right, example 3. Okay, so we have, again, a first order. Let's see. Let's see. Can we separate? Is this one separable? I don't think this one's separable. I'm just trying to figure out how to factor out the y there. Can't really do it, right? Because to be separable, you have to be able to get function of y times a function of x. Technically it is linear though. Yeah, it's linear, but that could get kind of ugly. I don't want to worry about that. So let's just use the techniques of this section. Pretty sure this thing is going to be exact, right? So in order to test for exactness though, you need to make sure to get it into that differential form. So we'll start with that. Take your differential equation and just treat the dy and the dx like differentials or variables. Move it into this kind of nice form where you have a 0 on one side, dx term first and a dy term, so that this will be your m function and this will be your n function. Is that okay? Okay, so first thing we want to do is just test. We want to make sure that we can find an f, a capital F, right? We want to make sure it's possible. So in order to do that, we're going to take the partial of m with respect to y, and that's what you'll get. And then you're going to want to take the partial of n with respect to x, and you do get the same thing. So verify that on your own. Okay. So, and you get the same thing. So that means that the starting equation, this guy's exact. And exact equations are good because it means that there exists a function f so that f equals c is the general solution. Okay, so we know a solution exists. So that means there exists this function f so that we have a general f equals c as a general solution. It also means that the partial of f with respect to x equals the m, and the partial of f with respect to y equals the n. And then it's your choice where you want to start, right? You can start with this one and integrate with respect to x first, and then partial differentiate with respect to y. Or you could start with this one, in which case you would integrate with respect to y first, and then differentiate with respect to x. Okay, so it just depends on whatever's easier, whatever you want to do first. So let's start off with this one first. So again, our goal is to find f. So it's given as a partial with respect to y, so we should integrate with respect to y. Okay, so if you integrate both sides of this equation with respect to y, like so, on the left, you'll have f plus an arbitrary constant, which could involve x's, right? And then on the right, if you integrate here, you're integrating with respect to y. So at first I thought that was going to be a little difficult, but that's a constant. So this works out fairly nicely. It's x e to the xy plus 2y and then plus some arbitrary function of x. This is your arbitrary constant, which gets absorbed from both sides. So I would say we're halfway done. We're pretty much halfway done. The only thing left to find is to figure out what that arbitrary function h is. And once you figure it out, we can plug it in and then we'll have f, and then we set f equal to c and we'll be done. Okay, so let's find h. So, we use this. We haven't used this yet. So I'm guessing we're going to take the partial of f with respect to x and then set it equal to this. Are you guys following the logic? Yeah? Okay. All right. So yeah, we're just going to take the partial of f with respect to x, set it equal to that. They both have to be the same. So what'll happen is when you take that partial of this guy, the partial of h of x with respect to x, that acts like an ordinary derivative, and we just set them equal to each other, you'll get this nice cancellation, which always happens. The ones cancel. Oops, not the ones. The e to the x y's cancel. The x e to the x y's cancel. And you're left with this very simple equation. H prime of x equals 1. So that's going to be super easy to solve for h. We'll just use direct integration. We'll integrate both sides with respect to x. On the left, we have h of x plus a constant c, right? And on the right, we have x plus another constant c. You could absorb the constants on the right side. So technically, you could write a c here, but you don't really need it, right? Because in the end, we're going to be setting f equal to a constant anyway. So here's f finally. So in order to get f, I took my h, which I solved for, and I just plugged it in right there. And there's f. All right. Okay, so there's f. So finally, just take f and set it equal to c. And this is going to be your general solution. And that's an implicit solution, right? Now, fortunately, on this one, you can actually solve for y, and you can find an explicit solution if you wanted to. If you solve for y, it looks like that. All right, so ideally, try and find explicit solutions. That's probably the best. All right, is this making sense why we would have one constant there? Does that seem reasonable? Why do we have one constant, c? Yeah, the original differential equation was first order. So yeah, if we got more than one constant, we'd have an issue, or less than one constant, right? If we had 0, that'd be an issue too. So yeah, we were expecting one constant. So if you graph the thing, it looks like this for different values of c. So there's a bunch of different values, and you could make a slider out of this if you wanted. It looks like all of these solutions span from -infinity to infinity. So we could put a slider and you can see each of the solutions like so. Okay, and they never go vertical, so we don't have to remove any points or anything. All right, you guys doing okay? We're just about done here. Okay, so what I'm gonna do, this last one, I'm just gonna set you up, and then I do want to talk about something before we leave. It has to do with unit measurements. All right, so here's a first order differential equation. So let's say I asked you to solve this one, right? The problem with this one is that it's not exact. It turns out that if you check for exactness here, we'll do it here. Look, this would be m and that's n, right? So if you take the partial of m with respect to y, you get 3x cubed cosine y. And if you take the partial of n with respect to x, you get 4x cubed cosine y. And those are not the same thing. So this should make you kind of sad, because it means that you can't. It means that this thing is not going to, the method for exactness isn't going to work here. All right, so you might try another method. You might try separating variables if it works, right? That might not work. Or you might try, using the linear techniques or direct integration. But, there is something we can do. You can always take an equation and multiply both sides by, say, a positive number or a negative number, and it won't change the solutions. Right? So what we can do is just take this equation and multiply both sides by 1 over x. All right. That's completely legal. You can do that whenever you want. Look, here's an example. Here's a very simple equation. X equals 3, right? All right, what if I take this equation and I multiply both sides by, let's pick a positive number, 5x equals 3 times 5. All right, don't these have the same solutions though? Have I really changed things by multiplying both sides by 5? I'll write 5 times 3. The solution's still 3, right? So you can do whatever you want to both sides. I mean, the one thing you can't do is you can't divide by 0, and you can't multiply both sides by 0. You can't divide both sides by 0. But look, we're doing neither, right? We're just multiplying both sides by 1 over x, and that's never 0, right? And we're not dividing by 0 either, because just make sure it's defined. Just make sure you don't choose x equals 0 and you're fine. So if you multiply both sides by 1 over x, what will happen is you'll take your original differential equation and you'll rewrite it like this. So make sure that that makes sense to you. I just multiplied the whole thing by 1 over x. Is that okay? Okay. All right. So now it turns out that this equation is exact. All right. Now you can test for exactness. This is your new m function, and that's your new n function. And if you take the partial of m with respect to y and the partial of n with respect to x, right? That's m and that's n. It ends up working out this time. So now this equation is exact. So the first question that goes through your mind might be, wait, like, okay, we can solve this one, but are the solutions going to be the same? Yeah, of course they are. You can do it, if you take an equation and you multiply it times 3, it still has the same solution. So if I multiply it times 1 over x, of course the solutions are going to be the same. Right? I'm writing down an equivalent equation. Right? So yeah, whatever we get for an answer should be fine. So if you do the work here, I'll let you guys work through it on your own. But what'll happen is this is the function that you'll find. There's f. Just do it the same way you did the previous 2 examples, and then set f equal to c. And then that's a solution, and it's a solution to both equations. So this is what we're after. It's a family of solutions. You could solve for y, but you'd need an inverse sine function, and then you have to worry about multiples of pi. So I'm not going to do that. I'll leave it like so. So here's your solutions. They look like so. And you could investigate this. I should probably not include 0. There we go. Okay, and you guys can play around with that. Yeah. All right, so that's exact equations. That's basically the general method. So before I let you guys go today, though, I did want to talk about one thing. So for those of you that are in my online class, I know I see 1 or 2 people that are in my on-campus class, but you guys don't have to worry about this on campus. But for online students, you guys have discussions to do every week. And so you guys have a discussion on exact equations, which, oh yeah, already got some answers here. And then you guys also have a short discussion on introduction to chapter 3, which is basically an introduction into modeling. I ask you a very simple question. This isn't going to require differential equations. It's about concentration. This is something that you do in a basic chemistry class. How many of you are familiar with combinations? Do you remember this notation here? Does that look familiar? Not at all. Uh-oh. Okay. Well, hopefully you saw this before. If not, you'll learn it on your own. We're going to use this when we study the logistic model for population growth. There's an exponential model called basically the Malthusian model, and then there's another model which is more accurate called the logistic model. And in order to derive it, we're going to use combinations. So I'm going to ask you to do a little research on that. And then also when we get to 3.4, we're going to talk about Newtonian mechanics. And when you're dealing with physics, right? So you have the, oftentimes, I mean, pretty much all the time, right? You're working with different units. For example, you might work with newtons or joules or watts or kilograms or meters or seconds or Kelvin or Celsius or candela or amperes or moles. There's a ton of them used in physics. However, there are only 7 base ones. These are the base 7 SI units that exist in physics, and every other unit of measurement is based on these. For example, a Newton is a unit of measurement for force. However, a Newton is equivalent to 1 kilogram meter per second squared. So it's a kilogram, a meters, and seconds. So every single unit you run across in physics at its fundamental core will be based on these guys. So why do we talk about these? Well, here's the thing. We've got 70 of these things, and these are actually give us most of physics is relied upon heavily by them. So for example, the kilogram, that's a big one. So you might ask, what is a kilogram, right? A kilogram is a unit of measure, or a unit of mass. But who decides what unit of mass is? Who decides how big this mass should be? So it's a good question, right? Someone at some point decided it. Why do they get to decide? What if I want to change it? Also, how do I mean, if they live over, let's say in France, and I want to create a weighing system that accurately measures, let's say, kilograms, how do I do that? Right? Do I have to write them a letter and then send me an actual physical kilogram so that I can calibrate my machine? I mean, I guess I could use someone else's. Maybe someone else, in the United States built a little weigh scales and I could use theirs. But don't I run into issues there? Because over time, well, they all just kind of get worse and worse if we're all kind of basing each other's results off each other's results. So you run into these problems specifically, let's say with the kilogram. Same thing with the meter. How long is a meter? We've got a meter stick in our class. It's about this long, right? Well, I mean, how do I know that's a meter? Who made that meter stick and how did they make it? Right? What meter stick did they use to compare to create the one that they created? So we have a lot of issues here. Same thing with a second. How long is a second precisely, right? We all have clocks, but clocks all have errors. So who has the master clock? So what I'd like you guys to do this week is to watch this video. So there's been recent developments in physics, and this video was made in 2013, but they've tried to move away from physical objects with the base SI units. They've basically tried to get away from having a physical kilogram. Actually, the kilogram exists, and it's in France in this like underground volt system. So if you really wanted to mess with the definition of a kilogram, you could go down there and break in and change it, right? But they've been kind of moving these over to universal constants, so not physical constants. And so what that allows us to do is basically allows us to avoid the issue of constants changing over time. It also allows us to, let's say, communicate these constants to, let's say, aliens living in outer space. If you want to explain to them what a kilogram is, you no longer need to send them a physical kilogram, which, by the way, by the time it got there, it would change in size anyway. So they could basically use the properties of the universe to derive it themselves. All right, so I put a video in there and I ask you to kind of discuss it. It's like a 10-15-minute video and there's some interesting stuff. And then if any of you happen to be taking physics now, I'm kind of curious whether there's any progress in this area. So if there is, let me know in the comments, but if not, it's not a big deal. Okay, let me turn this off. Let me stop here.